In this video, we're going to be working on a modified version of problem 5.18 from our textbook. This question asks us to calculate the output voltage of this op-amp circuit for 3 different input voltages. The way to approach this problem is we should try and find the general relationship between the input and the output before we go in plugging in these values for the input. So for now, we're just going to do everything in terms of Vn, and then we're going to plug in these values later. So let's get started. As is with any op-amp circuit, we're going to start off with our ideal op-amp equations. So let's just write them down. We have Vp is equal to Vn, and we have In is equal to 0, and Ip is equal to 0. So let's label these right here. This is going to be our voltage Vn at this node, and this is going to be our voltage Vp. Similarly, we have the current going into the inverting input In is equal to 0, and the current going into the non-inverting input Ip is equal to 0. So now let's examine this non-inverting input. We know that there's no current going into this input, and since this input only has one branch coming into it, there's no current going into that. There's no current flowing in that branch of the circuit. So because of this, we can simply say that our voltage Vp is just going to be equal to this voltage Vn. Whatever voltage is right here is going to be the same as the voltage that's at this input terminal. So we can say that. We can say Vp is equal to Vn is equal to V in. So now we know our Vp is equal to Vn, and by this relation, Vn also has to equal to V in. So let's say this is V in. Let me write it a little bit bigger. V in. So now we have a voltage V in at this node over here. Now let's use this part of the equation where we know In is equal to 0. So we can do a KCL at this node, assuming we have some current flowing in this direction called I1, and another current flowing over here called IF. If we do KCL at the inverting input of the op-amp, our KCL tells us that the current I1 flowing this way, I1, is equal to the sum of IF and IN, because I1 splits up into IF and IN. So I1 is equal to IF plus IN. But we know that In has to equal 0. So now we're left with the relation I1 is equal to IF. So we can now calculate I1 and IF. Let's start with I1. I1 is equal to the voltage across this 25 kilo ohm resistor. We know according to Ohm's law, I is equal to V over R, where V is going to be the voltage across this resistor. So we know at this end, we simply have 0 volts, because as you can see, it's grounded over here. So we have 0 volts on this end of the resistor, and on the right end of the resistor, we have the voltage V in, which is equal to Vn, which we calculated earlier. So what's going to be the voltage difference across this resistor, assuming we choose this direction of current? We can say that the current is going to be equal to the voltage difference 0 minus V in volts over the resistor 25 kilo ohms, which simplifies to negative V in volts over 25 kilo ohms. Now let's apply the same concept for the current IF. What's going to be the voltage difference across this 150 kilo ohm resistor? So assuming we choose this direction of IF, we can say that the voltage difference is going to be V in minus our output voltage. So the voltage difference is V in minus V out volts over the resistor 150 kilo ohms. So now we have our two parts of our relationship that we established. I1 is equal to IF. So now let's solve it. Let's plug these values in. We can see that negative V in over 25 kilo ohms is equal to our I1 is equal to IF, which is equal to V in minus our output voltage V out volts over 150 kilo ohms. This is our relation I1 is equal to IF. And now we know the value of V in. It's going to be one of these three. So let's solve for our voltage V out. So what's V out going to be? Let's multiply both sides by 150 kilo ohms, 150 kilo ohms. These two will cancel. This will become 1. This will become 6. So we have negative 6 V in is equal to V in minus V out. And just manipulating this equation, we can find that V out is equal to 7 V in. So now we have a relationship that we can use. We know that our output voltage is always going to be 7 times our input voltage. And just a side note, if this question had asked us to calculate gain, as we saw earlier in the introductory video, gain is equal to our voltage V out over our input voltage V in, which in this case would just be equal to 7. So they didn't ask us for that, but it's a good thing to know that your gain is always equal to your output over your input. So now let's start plugging in our values. We have this relation right here that our V out is going to be equal to 7 times our V in. So let's write that down for A. V out is equal to 7 times V in. And in A, they tell us that our input is 2 volts. So V out is going to be equal to 7 times 2 volts, which is equal to 14 volts. This is going to be our answer for part A. If our input is 2 volts, we're going to get 14 volts at the output of the op amp. One thing we should check, always it's very important, is that the op amp hasn't saturated. So let's check that. In order for the op amp to not saturate, this output voltage needs to be in the range of the supply voltages. Namely, the output voltage should be less than 16 volts because that's our positive supply, and it should be greater than negative 16 volts. And indeed 14 volts does fall in this range, so 14 volts is fine. We can use it. Now let's calculate part B. And we'll write down the same relation, V out is equal to 7 times V in. And we see V in is now equal to 4 volts. So let's plug that in. V out is equal to 7 times 4 volts, which is equal to 28 volts. Let's again check our saturation. Let's see if it has saturated. And indeed we can see it has, because we can see that if our output voltage is not in this range, it's going to saturate, and 28 volts is very much above our 16 volt limit. So now we know that this saturates. But what's the voltage? Even though it's saturated, it still adds some voltage, right? Well, since this saturated above, since it's above our positive supply, we call this positive saturation. And in the case of positive saturation, our output would just be equal to the upper limit, our positive supply. So in this case, V out would be equal to 16 volts. Now let's move on to part C. We'll use the same relation, V out is equal to 7 V in. And now they tell us that V in is equal to negative 5 volts. So let's plug that in. V out is equal to 7 times negative 5 volts. And this is equal to negative 35 volts. And let's again check to see if it saturates. And indeed it does. Negative 35 is less than negative 16. So again, this saturates. But now it saturates in a different region. It saturates below. In the previous case, in part B, we found that it saturated above 16. but now negative 35 is less than negative 16, so it's saturated below. And we call this negative saturation, since V out is less than our negative 16 volts. In this case, V out was greater than our 16 volts, which is why it's positive saturation. Negative saturation, so what happens in the case of negative saturation? Well, similar to our previous case, our output voltage would be equal to our supply voltage, but the difference is now, since we saturated negatively, since we saturated in the other region, we would say our V out is equal to negative 16 volts.